Hello everyone, Rugved Nakade here from TorsionalTraining.com. Welcome back. I hope you've been enjoying the course so far. We have explored some very basic torsional vibration theory so far, and we've also explored firing up diarrobes and modeling a very simple inertia stiffness model. Now, what I want to do in this particular lesson is I want to step through inertia stiffness system more because it's a very important concept, and it's really important because manufacturers do not provide shaft drawings. They consider it proprietary information. I have met a few consultants in the business that are able to convince them to give shaft drawings, but obviously those consultants have been in the industry for a very long time, so they can get that information easily. But for the most part, manufacturers do not provide the shaft drawings. Now, I will say one thing. I have heard a lot of experienced people tell me that it is always better to get the shaft drawings as much as possible, and the reason why is there are some very experienced people in this business, and what they say is they find a lot of discrepancies between the shaft drawings that they have and what they measure out in the field. So, my advice to anybody that's going to do torsional analysis, if you have the opportunity to be on the machine, if you have the opportunity to visit the machine, then take the opportunity to measure the shaft. And what I mean by measuring the shaft is measure the diameters, measure the lengths, and take any other measurements and any notes of important inertias and stiffnesses in the shaft, because there's been a lot of cases where what you have in the shaft drawings, what's provided by the manufacturers, does not necessarily match what's in the field. So this is a very important point. I can't stress this enough when you're doing a torsional analysis. It's really important to find as accurate information as you can about your shaft. So, moving on, the other point that's of note is that manufacturers typically do not perform torsional studies, especially in the case where they're not producing the whole train. And what I mean by this is, you may have a company like, say, a Caterpillar, which is an engine company. Now, Caterpillar does not necessarily know what is going to be driven by its engine. So, for example, it can drive a pump, it can drive a reciprocating compressor, it can drive an actual compressor, a screw compressor. Just depends on what it is. So, Caterpillar beforehand does not know what is going to be driven. So, they do not they do not design their shaft with by keeping that in mind. What they do when they design their shaft is to make sure that they have the most torsionally sound shaft. So typically what happens is the torsional studies are then done by the people that are packaging the driver and the coupling and the driven machine together, or in a lot of cases consulting companies do a lot of the torsional studies. So these are two things to keep in mind. So anytime you have a situation where you're putting together a machine or you're putting together a package for a specific application, a torsional study is extremely important. It's a must. It's written in all the standards, and if you're working for a company that is of known reputation, then they obviously know that a torsional study has to be performed in order to move on with their package. Now, the last thing that's of real importance is that manufacturers know that they're not providing shaft drawings, and so instead of providing shaft drawings, they go in and they calculate the inertias and they calculate in the stiffness information, and they provide it in a neat table like this shown here, which they call the inertia stiffness model. And what they do is they take their rotor, for example, take this rotor, and this is just an example that I came up with, and they have this stepped rotor, and they go in and they calculate the inertia, and they calculate in the stiffness for you, and then they plot it in a neat table for you, and this is the information that you can use to do your torsional analysis. Now, again, like I said, a lot of experienced people say that this inertia stiffness table comes pretty close to what is actually out there, but at the end of the day, it boils down to experience. It boils down to whether you can take real measurements in the field. But for the most part, these values can be trusted. But again, as a caution, remember that if you have an opportunity to get more detail, always go for more detail in a torsion analysis. So what they do is they take this shaft information and they convert it to inertias and stiffnesses, and then they produce this classic inertia stiffness diagram that you see in a lot of vibration textbooks. And they combine these calculations with a lot of shop experimental tests, and they confirm their inertia and stiffness values. And of course, when you're out there in the field, when you take your torsional vibration data from field data, then you have a pretty good understanding of whether your inertia, calculated inertia values and stiffness values are close to what the manufacturers have predicted. So this is the way they go. They don't provide you this information, but they do provide you the inertia stiffness table. So without further ado, I'd like to go ahead and model this inertia stiffness model. This is pretty close to a real system out there. I've changed up some values just to explain this a little better. And what you have is a motor that is driving a pump through a coupling, and the pump has an impeller. So, the motor manufacturer has provided this individual inertias and individual stiffness information, and the coupling manufacturer has provided their inertia and their stiffness value, and then the pump manufacturer has provided their inertias and their stiffness values. So the entire model that you put together is going to consist of the inertias and stiffnesses of each particular component in the rotor. So without further ado, let's fire up diarobes and let's go ahead and model this particular case study. And what we're going to do is we're going to shoot for calculating the torsional natural frequencies and the mode shapes for this particular model. See you in diarobes. Hi guys, so let's get started. I have this diarobes fired up here, and I've created this inertia stiffness model in an Excel spreadsheet, and of course this spreadsheet will be available on the website along with the diarobes file and the presentation. So I'll park this Excel spreadsheet to the side here so that we can use it as a reference, and I will fire up diarobes. And first thing you do, of course, is start with data editor like we did in the past, and of course you will start with your consistent set of units. So you got to pick your units. I have consistent English. Give it a description: inertia stiffness model of motor, pump, and coupling. Right, and then go ahead and click on material. Click typical steel, but of course don't forget this is an inertia stiffness model, so it doesn't matter. We're going to be setting all of these to 0 just like we did in the last lesson, and I always like to call them dummy material. And then after that, click on shaft elements. So the goal of modeling this is to show you how to model a full system using the inertia stiffness method. Now, unfortunately, since we're using the demo version, we're only limited to 5 elements, and in this particular model we have a total of 13 elements. So we'll not be able to calculate the torsional natural frequencies and mode shapes due to the limitation. But I will post the torsional natural frequencies and mode shapes so that you will be able to see what they are for this particular model. Now, if you happen to have the full model of the full version of diarobes, then you will be able to calculate the torsional natural frequencies and mode shapes. So click on element and type in element 1, sub 1, material 1, level 0, give it a random length of 10, mass ID 0, mass ID 0.001, stiffness ID of 0, stiffness OD of 0.001, and call that motor to motor. And I'll explain why I wrote motor twice. Before you do anything, click save. Close, yes. In my case, I've saved it as example-1. You can save it as example-1 as well. Now, here's one element, right? And this one element has 2 stations. It has station number 1 and it has station number 2. So, why I typed under shaft elements, why I typed motor to motor is because what it's doing when you type in an element, you're connecting two stations together by this element, and so this station is going to have inertia number one, which is here, right? And this station number two, is going to have station number two, right? And they are connected by spring number one, right? K1. So station number one to station number two are connected by element number one. So that's why, really, if I called this, if I gave this a description element, then the two that are connecting this element is motor to motor, right? So it's not as obvious here, but if I scroll down to this part where now the motor and the coupling are connected, then I would call this element motor to coupling, right? So same thing, um, but and in this case I would call this coupling to pump, and then in this case again it'll be pump to pump, right? Because we have a pump here, and then this guy will then be to pump to impeller. So that's very important in how you name your elements. It shows you where you are in the model, and I like to always name them descriptive, so I know that this is an element that only consists of motor properties, and this particular element consists of the motor and the coupling properties. So coming back to die ropes, we have a total of 9 elements, I believe, which are only connecting the motors. And then let's see, one element that's connecting the coupling to the motor. We have one element that's connecting the coupling to the pump. We have one element connecting the two pumps together, and then one element connecting the pump to impeller. So in all, we have a total of 12 elements. So let's model this. Element number 2 will have a sub 1, 1, 0, give it a length of 10, 0, 0 0.001, 0, 0 0.001, and again remember, it's going to be connecting from motor to motor. And this repeats for the next 9 elements, and your screen will look something like this. So you have a total of 8 elements for the motor, and I think previously I referred it to as 9 elements, but I made a mistake there. I meant to say 8 elements and 9 stations. So go ahead and click save after you type in all this information just like I have typed it in. Hit close, save data, say yes, and there you go. Now you have 8 elements and you have 9 stations. So this will belong to J1, that'll be J2, J3, and so on and so forth until you have J9, right? And if you come back to your mass elastic spreadsheet or your inertia stiffness spreadsheet, you will have a total of 1, 2, 3, all the way to 9 inertias that correspond to motor, right? Then going back, now let's go ahead and model the rest of this inertia stiffness table. So go back to model, data editor, click on shaft elements, and element number 9, 1, 1, 0, 10, 0, 0 0.001, 0, 0 0.001, and now it is going to be motor to coupling, right? Pulling up the spreadsheet again, we have element number 9, that's between the motor and the coupling, and the element is called motor dash coupling, right? Number 10, 1, 1, 0, 10, 0, 0 0.001, 0. That's going to be coupling to pump, I believe. Let me confirm this. Yes, coupling to pump, right there. And then the next one, 11, 1, 1, 0, 10, 0, 0 0.001, 0, 0.001. It's going to be pump to pump. last element is element number 12. 1, 1, 0, 10, 0, 0.001, 0, 0.001. I believe that is going to be pump to impeller. Right, so now you have a total of 12 elements and you have 13 stations, which corresponds exactly to what you have in the mass elastic spreadsheet. You got 13 stations right there, and you got 12 elements, right? So now, after you're done modeling up your elements, the next step is to then put in your inertias. So, just like we did last time, click on disks and it opens up this disk menu. Remember, we're dealing with torsional information, so it's a rigid disk, and station number 1 will have no mass, no diametral inertia, but it does have a polar inertia. So go back, and your J1 has a polar inertia of 60, so we put in 60, and ignoring the rest, you can call this J1. Similarly, number 2, it has 91, and I believe 1, 2, 3, 4, 5, 6, 7. The next 7 inertias, 2, 3, 4, 5, 6, 7. The next 7 inertias belong to the motor, so, and they're all 91. So your inertia table should look something like this, right? And then the last inertia in the motor, inertia number 9, I believe is 42, right? So we'll put 42, and that's going to be labeled J9. So after inputting all of this, close this, hit save, hit close, hit yes, and there you go. You have your first 9 inertias that have been put in to model the motor. So let's repeat this process for the pump and the coupling and the pump and the impeller. So let's go back to data editor, click on disks, rigid number 10 of course has a value of 45, so station 10, 45, and it's going to be J10, rigid 11. Your next inertia J11 is 15, and it belongs to the pump, so 15, inertia J11, and I believe the next one is also the pump, yes, and it has a value of 12, so J12, and last is the impeller, and I believe it's a pretty big, yes, 1050, it's a pretty big inertia, which makes sense. An impeller will have the largest inertia in the pump, and I believe it's 1050, so that's going to be J13. Hit close, hit save, hit close again, and there you go. All your inertias are modeled in. So now the last step is to model in the stiffnesses. So K1 all the way through K12, and let's go ahead and do that. So click on data editor, and then if you remember last time we clicked on torsional / axial, and this is a linear model, so click on linear connectivity, and let's get started on this. So T for torsional. Now remember, we're connecting station 1 to station 2, so going back here you have your K1 that is in between your station 1 and your station 2, so station 1 to station 2. Since it's torsional, we have a flexible stiffness, and your stiffness value is 7.5 e to the 8 inch pound per radian, so 7.5 e to the 8. There's no damping, and then remember, it is motor to motor, or you can call this K1, right? Torsional 2 to 3 flexible link 7.5 e to the 8 0, you can call this K2, and this repeats for the next 8 or 9 stiffnesses for the motor, and your final screen should look like this. Right, so I have all the torsion stiffnesses modeled in for the motor shaft, and each of them had a value of 7.5 e to the 8, so let's confirm that. See, we had all 7.5 e to the 8. Now let's put in the last few torsional stiffnesses. So torsional, that connects 9 to 10, flexible link, and now we're connecting the motor to the coupling. So we have 3.5 e to the 7. So 3.5 e to the 7, call it a K9. And I like to always remind myself where I am. So motor to coupling, 10 to 11, flexible link. Going back to the spreadsheet, we have 1 e to the 7, which is connecting the coupling to the pump. So 1 e to the 7, K10, coupling to pump. Torsional 11 to 12, flexible link. This is going to be connecting the two pump inertias. So that's 1.32 e to the 8, 1.32 e to the 8. That's K11. That's pump connected to the pump. And I believe the last one is the pump connecting to the impeller, and I suppose it's not a very stiff spring. Oh, it's pretty stiff. Okay, so 1.85 e to the 8, 5 e to the 8, and that's K12, and that's got your pump connected to your impeller. There you go. So hit OK, hit save, close, save, and there you go. You now have your full model in. Your inertia are here, and your torsional stiffnesses are all modeled in. And so this is your first inertia stiffness model of a pump, which is being driven by a motor through a coupling. Now, I'd like to show you how we would calculate the torsional natural frequencies and mode shapes of this particular model. Now, in your case, since you have the demo version, you will not be able to run this. So I'll show you how to run it, and then what I'll do is I will pull up the full version of Diropes that I have access to, and I will run the model and show you what the torsional natural frequencies and mode shapes look like, and I will post these mode shapes and natural frequencies as part of the lesson plan. So let me show you how you would do it. So you would click on analysis, you would click on torsional vibration, and remember you've got your natural frequencies and modes. So hit run, and now obviously it's going to give us this academic version limitation. I just wanted to show you that this is what you will see as a result of the fact that we have more than 5 stations, but nonetheless I will run it for you in the full model. Right, so I have the full version of Diropes pulled up here, and it looks almost exactly the same as what you have, and I will now show you what I do to calculate the torsional natural frequencies and mode shapes. So click on analysis. Now I know this is the part that you don't have access to. In case you happen to have the full version of Diropes, you can follow along with this, but I will post these natural frequencies and mode shapes on the website, so you'll be able to see how they look. So click on natural frequencies and modes, click run, and it solves. Click on post processor like we did last time, click on natural frequencies and modes, and click on mode shapes, and there you go. This is your first mode shape for this particular model, and I always like to animate these just to get a better sense. There you go. So this is your first mode, and you can notice that your first few stations here belong to your motor. So your motor is vibrating together. All the inertias are vibrating together, and the flexibility that you have is in your coupling. So let me go ahead and click on options and turn on the station numbers so you get a better idea. Clicking on station number, recall that the first 9 stations belong to the motor, and the 9th to 10th station connected the motor to the coupling, and then the coupling was connected to the pump, and then you have your pump, and then you have your impeller, which you can see has a much larger inertia. That's why you have a much bigger inertia symbol here than you do for the rest of these. And at the same time, notice that we had 7.5 e to the 8 spring stiffnesses, and then these spring stiffnesses were less. So in this model, right off the bat, you can see that what you have is a stiff motor that moves together, and then you have a very soft coupling connecting the pump to connecting the coupling to the pump. And so a lot of the flexibility that you have in this model is right here. So if you click on 2D view, you'll see this even better. So can you see that your motor is all moving together, but your flexibility here is in your coupling? And so your coupling is a lot more flexible than the rest of your shaft. So this is really the weakest link, is another way of thinking about it. And you have most of the flexibility here, and your first mode shape that it calculates is 19.84 Hertz. Now if you want to toggle to the next mode, you click on mode and you hit increment, and there you go. Again, notice that your flexibility lies in this region connecting your motor to your coupling and your coupling to your pump. And if you look at the 2D view, you'll notice that there is a little bit of phase difference in certain parts of the motor itself. Like you can see this inertia at number 7 is out of phase with this inertia at number 1. So in this particular mode, your motor is also participating in this particular natural frequency. Going on to the next one, now you can see that this is a pure motor mode, and one half of the motor is out of phase with the second half of the motor. And then again, you see a lot of flexibility where your coupling is modeled, but you can see that your pump is rather quiet in this particular mode. And clicking the next mode, now you have a lot of flexibility in the middle of the motor. You have some flexibility at the end of the motor, and then you can see that your pump is also waking up over here. So, but you see this is a rather high frequency, 348 Hertz. The possibility that we will excite such a high frequency, especially if it's an engine driven motor, it's pretty low. But again, it depends entirely on the application. In this particular application, I'll be surprised if we're exciting this particular mode. Truly speaking, the first 2 modes would be more concerning to me. So clicking on settings and typing mode number 1 over here, it brings us back to mode number 1 right away. And you can see that mode number 1 would be a really concerning mode because you have a lot of flexibility in the coupling. And the way to interpret this is, if you have a machine that has a torsional vibration at this natural frequency, all your motor is going to move together, as you can see, and all your pump inertias are going to move together, and you'll see the flexibility in the coupling. So really the most likely place that you will have a failure will be in this coupling. You will see a lot of stress in this coupling, and this is where your failure would most likely take place. If you were to toggle to the next mode, in this particular case, if we had the torsional natural if this machine was running at the torsional natural frequency of 144 Hertz, then again you will have your motor, and you may have some high stresses here, but really again the flexibility is right here, and so you're most likely going to see a failure in this particular region that's connecting the motor to the coupling. So there you go. This is module number 2, lesson 1. Again, I will post these mode shapes for you to check out and understand, and I will post the diaropes file. I will post the Excel spreadsheet for you as well, so you can model this in yourself. If you have any questions, of course, feel free to get in touch with me anytime, and I'll be more than happy to work this exercise with you. Talk to you soon. Take care.